Evaluate the limit of this function cn plus d raised to power n 1 over n and tell whether it is converging or diverging. And the limit is given like d is greater than c is greater than 0. It means d is greater than c and both of them are greater than 0. Both of them are positive in nature. Let's apply the limit. Limit n approaches to infinity, c raised to power n plus d raised to power n whole raised to power 1 over n. Limit n approaches to infinity. I can take d common outside. For example, if I want to take d common outside, it will become, if I take this dn common, it will be cn over dn plus 1 and the whole power is 1 over n. I can separate it into two parts like limit n approaches to infinity d raised to power n into 1 over n and then c raised to power n over d raised to power n plus 1 raised to power 1 over n like this. This will be cancelled, so there is no more n here. We can move it outside like this. So it will become d limit n approaches to infinity c raised to power n, or we can write it like c over d raised to whole power n plus 1 and this whole power is 1 over n. We can write it like this as well. So this thing basically, this function that is d limit n approaches to infinity, you can write it like this or you can write it like this as well. It's up to you. What do you want to write? This is 1 plus c over d raised to power n whole raised to power 1 over n. This thing is basically equals to d into 1. How? We know that it is given that d is greater than c is greater than 0. It means their ratio, that is c over d. Since d is greater than c, so it means it will be less than 1. Since it is less than 1, so there if we take its power n and limit n approaches to infinity on it, this will converge to 0. So this upper limit, this thing is converging to 0. So it will be 1 plus 0 and 1 over infinity is also going to 0. So anything having power 0 will give you the answer 1. So here we got the answer of limit equals to 1. 1 into d, that is d. So the sequence converges. The sequence converges to d here. Question number 18. 5 raised to power n over n plus 1 whole square. Limit n approaches to infinity 5 raised to power n over n plus 1 whole square. We can use the L'Hopital rule here to simplify the terms, the numerator and the denominator separately. In the L'Hopital rule, you have to differentiate the numerator separately and differentiate the denominator separately. You know that d by dx of a raised to power x is a raised to power x ln of a. So here d by dx of 5 raised to power n is 5 raised to power, this limit you have to write this limit as well, limit n approaches to infinity 5 raised to power n ln 5 divided by the derivative of this denominator will be 2 into n plus 1 like this. Again we can reduce this denominator by taking the applying the L'Hopital rule and taking the derivative of the numerator and the denominator separately. It will become ln 5 is a constant, it will be written separately. Take the derivative of this 5 raised to power n, that will give you the same answer. 5 raised to power n ln 5 divided by 2 into 1 plus 0 like this. Now n is reduced here. It will become limit n approaches to infinity 5 raised to power n ln 5 whole square divided by 2. Now if you apply the limit here, 5 raised to power infinity will give you the undefined answer. So your sequence in this question diverges. Sequence diverges here in this question 18. Now question number 19. In question number 19, we have 1 plus 1 over 2 factorial plus 1 over 3 factorial plus up to 1 over n factorial. Now this question number 19 is basically the geometric series. If you observe it, let an equals to 1 plus 1 over 2 factorial plus 1 over 3 factorial plus up to 1 over n factorial. I am naming this sequence equals to an. Then an plus 1 will be 1 plus 1 over 2 factorial plus 1 over 3 factorial plus up to 1 over n factorial plus this extra term that will come here, that is 1 over n plus 1 factorial. This thing is basically these terms is basically an, that is the same thing, plus this ending term is 1 over n plus 1 whole factorial. You see that this thing is greater than an, because in an some more term is adding up here. So this whole thing is greater than an. So from here we can say like an plus 1 is greater than an. This shows that the sequence is increasing. Sequence is increasing. Now we need to check, because I'm just solving this question with some other approach, like if the sequence is increasing and if it is bounded, then it will converges to some limit. Then it will have some upper bound as well, and that it will converge to some limit. I'm approaching that method here in this question. So the sequence is increasing. Since the sequence is increasing, we need to check whether it is bounded or not. Now to check whether it is bounded or not, consider, you know that n factorial. N factorial is basically 1 into 2 into 3 and up to n. It is this thing. If we have 2n minus 1 factorial, this is 2n minus 1. It can be written as 2 into 2 into 2 into up to 2, that is basically n minus 1 times, because it is mentioned here n minus 1 times 2. Now you see this 2 into 2 into 2 into 2, this product will be less than this product. So we can write it like 2n minus 1 is less than n factorial. And if I just take the reciprocals, if I write it like 1 over 2 raised to power n minus 1, that this sign will, inequality will change, and it will be this less than will change into the greater than 1 over n factorial. Because you know that 2 raised to power n minus 1 is less than n factorial. You see, like if 2 is less than 3, then 1 over 2 will be greater than 1 over 3, because this 1 over 2 will be like it will be 0.5, and if you will divide it, it will be 0.3 or something like that. So after taking the reciprocal, my inequality is changed here. So we got from here that if we can write this thing like 1 over n factorial is less than 1 over 2 raised to power n minus 1. Now I know that what was my an. I will use this thing result later. Now what was my an? My an was the same thing that was given in the question. My an was 1 plus 1 over 2 factorial plus 1 over 3 factorial plus up to 1 over n factorial. You know that n factorial, 1 over n factorial is less than this term. So if I replace this term with this one, so this whole thing will be less than that. So this whole thing is less than 1 plus 1 over 2 plus 1 over 2 square, because it is, I am following this thing for 2n minus 1. 1 plus 1 over 2 plus 1 over 2 square plus up to 1 over 2 raised to power n minus 1. You know that this is the geometric series. This is the geometric series, and you are given that in a book of first year, that is, I have that book with myself, that is the first year book for the mathematics, this one book, and in that book on the page number 210 you are given with the sum of the geometric series formula. This one, two formulas. If your ratio is less than 1, then you are going to use this formula. If your ratio is greater than 1, then you can use this formula for the sum of the series. Using that formula here, you know, first of all, you know the ratio. How you are going to find out the ratio, that is r is equals to the second term divided by the first term, and that is equals to 1 by 2, that is 0.5, and that is less than 1. So for sum of the geometric series Sn, that is the sum of this geometric series, we are going to follow a into 1 minus r raised to power n over 1 minus r. Now a is this first term, r is your this common ratio. So the sum of the geometric series, this an that was less than this thing. So the an basically, this an is less than this sum. And what is that sum? A is 1 here. 1 into 1 minus r raised to power n. What is my r? That is 1 by 2. So 1 over 2 raised to power n divided by 1 minus r is 1 minus 1 by 2. And we can simplify it. That is basically equals to 1 minus 1 by 2 is 1 by 2. 2 will be taken up because it is 1 by 2 in the denominator. It can be moved up like this. So I got 2 into 1 minus 1 over 2 raised to power n here. And you know that we can just open it as 2 minus 2 over 2 raised to power n. So this will be 2 minus 1 over 2 raised to power n minus 1. And you know that this term is getting minus from this 2. So it means the whole answer will be less than 2. So this 2 is basically the upper bound of this thing. So it means it is bounded because it has some upper bound. Hence we can say an is bounded. Also we know that 1 plus, if I just write this whole an term with this 1, if I write it like 1 plus 1 over 2 factorial plus 1 over 3 factorial plus up to 1 over n factorial. I know its formula. That is basically, that converges to always e when n approaches to infinity. This thing, not the same question, not the same question, whole question. But if this whole question is added with 1, this typical sequence converges to e when n approaches to infinity. And what my sequence was? My sequence was 1 plus an. This thing is an. That is converging to e. So if I take an from here, so an will converge to e minus 1 when n approaches to infinity. So it means this sequence is converging and its limit is basically equals to e minus 1 here. Now question number 20. In question number 20, we are given with first term a1, that is under root 2, and the n plus 1 term is under root 2 plus an, and my n is greater or equals to 1. Now my a1 first term is under root 2. I know that this under root 2 is less than 2. Assume that, now we need to suppose here something. Assume that an is also less than 2 for some n is greater or equals to 1. Then we can write an plus 1 whole square is equals to, if I take the whole square of this an plus 1 term, this will be equals to whole square under root 2 plus an. This will be equals to 2 plus an. And this, you know that this an is less than 2. This an is less than 2. So less than 2 term, less than 2, if added with this 2 will be less than 4. It is obvious. So it means an plus 1 whole square is less than 4. So this shows that an plus 1 is less than 2. So the sequence is bounded and its upper bound is 2. Thus, the sequence is bounded. Now we need to check whether it is increasing or not. And its upper bound is 2. For that purpose, whether it is increasing, monotonically increasing or not, you need this term, an plus 1 whole square, and you need an term. An plus 1 whole square minus an term. This will be equals to, you know that an plus 1 whole square is equals to 2 plus an. If I take the square of this an plus 1 term, I will get 2 plus an, and here I have an square. If I just factorize it, I will get here 2 minus an into 1 plus an. This thing is always greater than 0 because you know that an is less than 2. An is less than 2. This term is less than 2. So the answer cannot be negative here. So this whole thing will give you the answer greater than 0. So it means the sequence is monotonically increasing. Now we need to find out the limit. For that purpose, limit n approaches to infinity an plus 1. This is equals to limit n approaches to infinity under root 2 plus an. I can write it like limit n approaches to infinity 2 plus an whole power 1 by 2. Like this, because this thing has the power 1 by 2. If let's suppose the limit of the sequence is L. Let's suppose I'm giving the name to the limit. Let's suppose the limit of the function, the sequence is L. I'm replacing this limit with L. So here I will get under root 2 plus L. So squaring both sides, I will get L square equals to 2 plus L. So here I will get L square minus L minus 2 is equals to 0. Now factorize it, I will get L plus 1 into L minus 2 is equals to 0. So it means either L is equals to minus 1 or L is equals to 2. It is given that limit is basically greater than 0 because here you see that it is bounded above by 2 and also it is monotonically increasing, so the limit will be greater than 0. So it means this is not possible. So my sequence is convergent. Sequence converges to 2. So this is the answer for your question number 20.